Live from the Key TV studio to your TV and on the web, it's Homework Hotline. Go to homeworkhotline.tv to ask your math or science questions.
Hi, welcome to Homework Hotline. I'm Ken Pinkerton. I'm a retired science teacher from Zane Middle School.
And my name is Reada McConnaughy. I'm a math teacher with Northern United-Humboldt Charter School, and you're watching Homework Hotline.
Homework Hotline.
Thanks for joining in.
Yeah, definitely. We're here to answer your math and science questions, so you can contact us by going to
homeworkhotline.tv. So that website.
Follow the leads there, and then you can send us your questions or just let us know that you're playing. I want to say hi to Eden Harris, who is in Colorado, who I hope is going to be joining us today.
Eden.
So, so we're not real.
Yeah, we are.
Or we are Eden?
Yeah.
Okay.
There was this voice in the
voice,
sky
I know,
that
was
said,
the one.
hi,
So,
Eden.
and then we have a cool thing we want to remind you about. Key to sponsoring My Family Flavors Contest. And do you have a favorite family traditional recipe? And if you do, Keat wants to know about it.
Yeah, please go to keat.org and you'll see the details and the rules, and there's an entry form. You need to be ages 14 to 24. And if you are under 18, you'll need a parent or guardian's permission. But you could be chosen as one of the 3 winners who will cook their dish on TV and win a $100 gift card to a grocery store.
So you could get fame and fortune with the same great recipe.
So submit your recipes by November 13th.
Definitely so.
At keat.org.
I would love to be on the taste test committee.
Taste test? Oh, I wonder
good.
if we could both do that.
That would be fun. So if you have your questions, send them in. So on Tuesday we started talking about pendulums, which pendulums are kind of arms or legs that hang off of something. And we talked about the properties of them, which are surprising, is it's not the weight that goes on the end of a pendulum, but it's the length that determines whether it's going to be fast or short. Mm-hmm. So you can see that these are significantly, I think they're half, this one is half the length, and right now they're kind of matched up, but it's considerably faster. And then we have this daring, wonderful demonstration, which you should not do at home.
Hold on,
which
I gotta
is
go grab it.
The bowling ball pendulum. So this is a neat demonstration because it shows several things. The most important one is that because of friction, the bowling ball loses a tiny bit of energy. So Rita's going to hold it up quite close to her head.
To my face.
And then when she's ready, she's going to let go and hold very still.
Okay, don't lean forward, right?
Don't lean forward, don't move.
And this isn't something you should try at home with a bowling ball?
No.
Okay.
And you don't push it either. So.
Oh, phew.
And so you'll see that it comes close, but every swing is a teeny bit less.
A little bit shorter?
A little bit less, yeah, because of the friction of the rope.
So I'll try to go just by my chin.
Yeah.
Don't give it any push.
Nope.
Just let go.
Right.
Ha ha. Okay. That's pretty good.
Anyway, so it's a neat demonstration of, and the length of the rope that we have hanging from the studio is the thing that determines the period or how fast or slow that swings.
I think it's interesting. How did you get this screwed into a
I just drilled into it
ball?
and then threaded it, and so it's that's my I love the colors of that ball. It's
drilled into it with like a regular drill?
Yeah, a regular drill,
Cool.
and then just threaded it. So they're pretty cool. So. All right, so again, you can go to homeworkhotline.tv and send in those questions and see. It says, I think we got something from Nathan White.
Nathan White, what grade are you and what school? Pretest, okay.
It's got pretest information. Cool.
So it says, hi, I got my pretest back today and could not figure out how to do y equals 3x plus 60. I would be happy to help you.
Nice. That's a good one.
Y equals.
And then also, let us know where you're from.
And Nathan, just question, do you have to solve for x? Do you have to graph it? Do you have to graph this equation? So if you could put that on there. And this really reminds me of slope-intercept form. So I don't know if that's something that you're working on right now. Y equals mx plus b. And if you have to graph this, your m is your slope. So the rise over the run of your line. So slope. B ends up being where it crosses the y-axis, so we call that a y-intercept. So when you get a chance, can you let me know, did you need to graph this, or did you need to, sometimes you might even have to solve for x, so get x by itself instead of having y by itself. Maybe I have to scroll down. Nope. Let's see, what do you think? Do you think you had to solve for x or graph it?
When I first looked at it, I thought solve for x.
Solve for x? Guess. Okay, well, we'll do that real quickly. I usually think of, if I want to get a variable by itself, what am I doing to that variable right now? Oh, graph it. Okay. But you would think what you're doing to the variable and then undo that with inverse operations. So instead of multiplying by 3, divide by 3 each side, or subtract 60 to get a 0. Okay, but you said to graph it, so let me try to get a graph on here. Okay, and if we have our y-intercept, that's going to be the first place that you start when you're going to graph. So on the y-axis, where would 60 be? Well, we probably don't want to make each line be 60, or 1, but maybe each line could be 10. So 10, 20, 30, 40, 50. Looks like I need a little bit more space to get 60 up there. Okay, so let me extend that. And if your y-intercept is 60, and did I read that right? Yep, 60. That's where you're going to put your first point. Be right here. Okay, that's your y-intercept. That's where it crosses the y-axis. Next is your slope, which is 3. And a lot of times, I make 3 look like it's a fraction so that I can remember that it's the rise, the vertical, over the run, the horizontal. Okay, so the rise over the run. So from 60, we want to go up 3 over 1, up 3 over 1, all the way along here. But you know what? What if I multiplied 3 by 10 and 1 by 10 and I got up 30 over 10? That's going to fit our graph a little bit better. Okay, so from 60, I want to go up 30. Try my other color here. 70, 80. So sorry it's not perfect, but that's okay. You don't have to have perfection necessarily in math. So up 30, so up 10, 20, 30 over 10. And just mark down here on the x-axis that each line would also go by 10, if that's what you need. Okay? So put in the chat here if you're understanding what I'm doing and if it's helping you, or if you have a different point of confusion or a question.
And then if you
oh yeah,
them.
Thank you. Will you hold that
Sure.
for me, please? And then your 2 points, you can make your line or your graph that you're going to need. And it's always better, thank you. It's always better to have a straight edge or a ruler. You could use the side of a piece of paper, or even a Post-it note to make your straight line. So let's see here if that shows up on the camera. Looks like it is. Okay, so this is what I think you needed to do with graphing it. Start with your y-intercept, put that point there, then take your slope, which is the coefficient or the number times x and change it so it's a fraction. You can even make it bigger if you need to by multiplying both by the same number, okay?
And that's a great trick when you have something as big as
60.
60. Yeah, that's very clever. Very good.
Okay.
Otherwise, you'd be doing little tiny increments.
All right, well, I hope
Nice.
that helped, Nathan, and hope you do much better on your test.
So an
Okay.
8th grader. Very cool. Thank you, Nathan, for calling. That's great. All right, so we'll wait hopefully for the next one. Or is there one?
Helped a ton. Awesome. Okay.
Oh, nice. It helped a ton.
He said it helped a ton.
Oh, helped a ton.
It'd be kind of fun if you said it helped a 10.
I know, that's what I heard.
All right. Pendulums, huh?
Pendulums. All right, so here's one we briefly talked about, one that you can make at home that's kind of neat. And it's called a coupled pendulum. And so with this one, you'll notice it's different because it's got, the support is a string. Okay, and then I just made little pendulums out of film cans, but I could do anything. I could use, let's try it.
You know,
with
we don't use these very often. These little
the little film cans anyway. No, they were the best. But, okay, so we'll try it. We'll go.
film containers.
Film containers, right. It's the old 35 millimeter film came in them. So we'll try it with washers. And then I just made these with, I took coat hangers and bent them so they're the same size.
Okay.
And then the neat thing about them is, that so with a couple pendulum, if I let one go, they're kind of magical in that now they're both swinging. The first one stops,
They're like,
and now it's going again, and the second one stops. And so the energy of the pendulum is transferred through the line down to
through the string
through
here?
the string, right? Yeah. So you'll see that the string is oscillating or moving kind of back and forth. And then this is a commercial one that's even cooler.
Ooh.
'Cause it's
This is
shiny.
one you put on your desk at
Yeah,
school, huh?
Right. And then we're going to start one of these. So I'm going to start, I'll stop them. And you'll notice that the second one is starting to pick up quite a bit.
Oh.
And
You know, this part up here is much firmer,
it's
right?
more
than
rigid,
the string,
right?
More
But
rigid.
but it's hanging. So I think that you'll notice the energy's going down that and making it move quite a bit. So now the first one is stopped and the third one is going big, and then second one. So the energy is transferred through those, through the bar. So
Through this bar up
yeah,
here?
through the bar up there, through the wiggling of that. And so I think those are cool.
What if you held that
You could try.
firm?
It's a good idea. It will stop it. And if you hold
Okay.
it real still,
Okay, I'll try.
let's see if that.
I can feel it moving, but
Yeah,
I'm
but
not letting it go to the other one.
Right to the other one. So it's the second one's swinging, but it's not
Alright.
like. Yeah, so it's definitely the moving bar on there. So, and this is one you could make too. It's just hang the bar, maybe a pencil on there. Have to work on one, but that's another.
And what were the balls?
This is one commercial. So these are just ball
Oh,
bearings. that are-
commercial.
Yeah. So
Commercial means you bought it.
yeah, somebody. The cool thing about being a science teacher is people give you really cool gifts
I bet they
all
do.
the time. So a lot of these are.
And you can't call it hoarding, right?
No, it's for it's for the children.
Oh,
My wife loves that one.
yeah, I bet she does.
So those are another neat pattern, and this is another commercial one that that shows the pattern. And what I think is especially cool about this is it shows how the energy is absorbed and it's recorded in this. So I don't know if we can do a sky cam or not. I'll try and put it in the middle for number one. And so I'll take out the pattern here first. I'll try to. And then this one is, you notice the way it's hung is differently. It's got two pins up here and then also one there. So if I get it going.
Reminds me of a heart.
Yeah.
Is this also a commercial one
Yeah,
that you bought?
this is one, right. And
Okay.
this is also, I think they got this one from Karina Junga, who's one of my co-teachers at Zane.
Wow.
And so you can, the really cool thing about this is you can see how the energy is going down. So it's getting smaller and smaller, and it makes because of the friction of the sand and the air, it makes a neat pattern on top of this. And then at the Math Festival and the Discovery Museum, I have a thing called a Harmonic Graph, which is,
I have a question coming up, but
okay.
you go ahead and, if you don't mind, finish
not
what
at
you're
all.
doing. It'll take me a little bit to write
that-
this on the board.
and actually let me try to put this on maybe even better than it was. Might have to lower the sand. But you'll see there's 2 sharp points right there that it's hanging in. And then I've got too much sand now. So what's the question?
All right. It says, the least common multiple of the consecutive positive integers from 20 through k is greater than 1 billion. Oh boy. Okay, so assume that k is greater than 20. What is the least possible value of k?
So it's the least common multiple of 20 and
Yeah.
another number?
So least common multiple
Of 20?
consecutive positive integers from 20 through any number, k,
Uh-huh.
and k is greater than 1 billion. Sauce man, what grade are you in? And
Well, the neat thing about these common multiples is with factors, and you
Yeah.
come down to prime factorization. So if you did,
multiples of 20,
right?
20, 40, 60, 80, and so on, right? 9th grade.
9th grade, it says
Okay. So
So
least
the
common multiple of consecutive positive integers
from 20 through,
through k is greater than 1 billion. Huh. I'm not sure.
so I think,
Is this a
so it
story
I think,
problem,
yeah,
you
it
think?
seems, so the way I'm reading it is the least common multiple of 2 numbers, the least common, that are consecutive, right? So that would be like 21 and 22, right?
Consecutive positive.
Positives, right?
So you have one integer and then the next integer,
X plus 1, right?
x plus 1, that means consecutive,
Right.
okay? Least common multiple,
Well, it would be, the least common multiple would be x, wouldn't it? Because that would have to be, well, no, because that wouldn't go into the next one.
the greater than 1 billion is kind of what,
Like, yeah, that's throwing me off too, so I'm not sure. I'm going to read it again. Put on my glasses.
thank you, yeah.
Excuse- Okay.
You know, and I wonder if it's taking consecutive integers times each other, so like x times the quantity x plus 1 would be the one right after it, and then saying that that is greater than 1 billion. I don't. Do you have more information that you could help us?
Yeah, we're not
So
sure.
type a little bit more on there. I'm stuck as well. Did you get somewhere with it? Maybe you could
The
tell
least
us what you
common
got.
multiple of the 2
Okay.
over 20,
Yeah. I'll keep looking at it, and if I
right? Well, if we did like, let's take 20 and 21, what would be the least common multiple of 20 and 21, just to show people how you find these common multiples?
okay. So 21, right? Well, I know that 20 times 21 is going to give me a common multiple
Right.
between the two. So that's why I was thinking x times the quantity,
Right.
x plus 1, 20 or 21,
Right.
right? And then greater than 1 billion.
But greater than 1 billion.
So I was just doing this with my daughter last night.
Would
How
it
do
be
you,
would it be 1 billion and 1?
so 100,000 million. I need
Okay.
one more for billion. So
Right.
100,000 million.
Or thousands, 10,000, yeah, right. Yeah,
Oh
you got
boy.
it right. Yeah, that's right.
Don't look! No, I'm kidding. Okay, this is
That's
100, 1,000, 1 million.
And then million, right, 1 million.
1
Billion,
billion.
right. That'd be 1 billion.
There.
Right.
Ha.
Okay.
Okay, we got
Right.
9 zeros, that's 1 billion. So I think this is how you would show it. Least common multiple, meaning you multiply the two. And if they're consecutive integers, one was right after the other. The first one is x, next one would be 1 right after it. So add 1,
Right.
okay? Hopefully that helps.
Yeah.
I'm satisfied with it. So, and if you have more information to add, you know,
Yeah.
type it in
Yeah, or if that seems right,
chat for us.
let us give us some feedback on what we think there.
You know,
So-
you might even have to go ahead and multiply this out, which x times x would be x squared, and x times 1 would be 1x, but we
Right.
don't have to write the little 1. It can stay invisible. So greater than 1 billion. 1, 2, 3,
Right,
with 9 zeros. Okay?
that works, yeah.
Okay.
Okay, and I think it would, okay, so let me.
Oh, you're stuck on it now,
refresh.
excuse
No,
me.
but what, if I did this, wouldn't it be 12, wouldn't I just add this in front of that, except take out that 0? So if I did this, I don't know, okay, I'm gonna do this. I'm gonna mess you up. Okay, I'm gonna go.
Are you
go
doing
on.
1 billion?
Yeah, I'm doing 1 billion times 1 billion.
Didn't
and
I do 1 billion?
1 billion, and I'm multiplying it times each, a billion times a billion and 1?
No. I don't think so.
No?
Are
Okay.
you trying to solve for x?
Yeah, that's what I was, well, I was trying to solve for what the number is if you get that.
Oh, do you need an actual, if you need a number for what x is, like you need x by itself, because you have x squared, that turns it into a quadratic. And so to solve quadratics, you get one way to solve them. You get everything on one side of the equal sign, or in this case, the greater than sign. So subtract 1 billion from both sides, and I'm going to get x squared plus x minus 1 billion, a 1 with 9 zeros. Bring down your sign. It didn't quite line up like I should have had it line up. And then you have a 0 over here because you did 1 billion minus 1 billion is 0.
Okay.
This side minus 1 billion, it would no longer be, or it would be right here minus 1 billion. Leave this alone. And then you could use the quadratic formula. Does that sound familiar? You could try factoring it. I don't think it's going to work. You could complete the square, again, quadratic formula. If you have learned that already, some countries just teach you the quadratic formula. They don't teach you how to factor. They just do quadratic formula because it will work every single time. Negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. Okay? And you would pull a is whatever's in front of your x squared, which is a 1. B is also an invisible 1. And then C is negative 1 billion. Okay? So I'm not sure if this is how far you have to take it or if you just needed the inequality. But to finish this off, you would plug in 1 for A, 1 for B, and negative 1 billion for C, and then simplify this. Just remember your little plus or minus over there. So, okay.
Cool, sounds good.
Oh, I do see some more on here. I think we're getting short on time. We better talk about my family, my flavor, real quickly.
And again, if you have a family favorite traditional family food or a recipe that you just love, it could be any kind, dessert, main course, a salad, then Keith wants to know about it. So you can enter My Family Flavors Recipe Contest. And then the cool thing about it is that you get to then share that recipe, probably be recorded here in the studio, so you're not totally on the spot like live, and you get a $100 gift certificate. So check it out, and so go to keat.org for more details. And I think it would be
Deadline
cool
to enter is November 13th, so that's about a week away.
Yeah, it's coming up fast. So.
Okay.
And I've got two things I'm hoping
Okay,
to get in,
great.
so let's get
I
the
hope
big
so.
one in. This is a cool,
You mean you didn't want to end with my arm as a pendulum? Oh, yeah.
let's get this
Okay.
guy. So I'm going to have that.
Should we lift
I'll
up
go- yeah.
over?
So this is
Okay.
called the Wave Pendulum. And the neat thing about it is that it's a series of pendulums that are all slightly shorter than the other. And then I think I've got it on the wrong side, but we can light it up.
That's okay.
And so it shows some neat patterns that happen. So I'm going to swing them all at once. And as we go, you can see that they kind of snake and they'll go into sequence and all that. So I'm Ken Pinkerton, and we'll have a new group here next week. So enter the contest. Definitely so.
Yeah. Join in live on homeworkhotline.tv.